Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're looking at Chapter 6 of Thermodynamic Properties of Fluids, and we are specifically looking at fundamental property relations and natural variables. So in this, I have du is equal to TdS minus PdV, and we derived this from the first law. But if we think of this as a differential, you'll go back to your calculus days, then you get u is a function of S and V, right? Those differentials there indicate this. I also then had dH is equal to TdS plus VdP. This came from saying that H is equal to U plus PV by definition. And in this case, I get H is a function of S and P. I can define A as U minus TS, getting me dA equals minus S dt minus PdV, which indicates that A is a function of T and V. And Gibbs energy is H minus TS, or dG is minus S dt plus VdP. So Gibbs energy is a function of T and P. Now, if you look at this, these variable choices for U and H are somewhat unfortunate because they are based on entropy, which is the least understood of all of our properties. But A and G have their natural variables that are measurable, temperature and volume or temperature and pressure. Our goal is that we're going to be able to evaluate any of these from measurable quantities, pressure, volume, temperature, using simple mathematical operations. So we need a quick review of some mathematics. So if you'll recall from our exact differential definition from mathematics, that I can say that df is the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. Or I can call this m dx plus n dy, where m is the derivative of f with respect to x holding y constant, n is the derivative of f with respect to y holding x constant. And if I take the second differential, or second derivative rather, of f with respect to x and y, I could do it in either order, which means that dm dy has to equal dn dx. Now we're going to take advantage of that. We're going to use this to develop mathematical relationships that are these second derivatives. And they're going to be called the Maxwell equations, from the person who originally noted this. So if you start with the fundamental relation for u, for instance, du equals TdS minus PdV, then T is du ds, holding V constant. And negative P is du dV, holding S constant. We can take the second order mixed partial derivatives. So I can do this as the derivative of u with respect to S and then with V, which gets me dt dV at constant S. Or I can do the derivative of u with respect to V and then with respect to S, getting me negative dP ds at constant volume. These have to be equal to each other. So this last thing where I just simply said, oh, they're equal to each other, this is a Maxwell relation. dt dV at constant S is equivalent to dP ds, negative dP ds at constant volume. And we can do this from each of the fundamental relations. So if I look at this, this is the one that we first derived. S and V are the natural variables for U, so this came from the U fundamental relation. Sorry, my mouse is going crazy today. This one, P and S, this must be H. It's a natural function of S and P. dt dP at constant S is dV ds at constant P. V and T, this one comes from A, the Helmholtz energy. ds dV at constant temperature is dP dt at constant volume. And finally, P and T are Gibbs energy, gives us negative ds dP at constant temperature is dV dt at constant pressure. Now, I recommend that you go back and just choose one of those other fundamental relations and see if you can derive one of these Maxwell relations on your own. We'll come back in the next lesson and see how we can use these.